Hello. Now we are going to look at constructing or finding the orthocenter of a triangle. So when we want to do this algebraically or using coordinate geometry, what we need to do is think about how we would construct the orthocenter. How would we draw it out accurately? So if I have my points A, B, and C, I draw out my triangle, and the orthocenter, ortho means orthogonal, so at right angles. So I'm going to go at right angles to one of my sides through the opposite vertex, through the opposite corner. So L1 is perpendicular to AC through the opposite corner B, or through the opposite vertex B. And where those orthogonal lines cross over is going to be my orthocenter. That's how I construct my orthocenter, so that's how I'm going to find it algebraically as well. So if we can tell ourselves the story of this question by drawing our diagram and saying, well, how would I construct this? Then I can follow all of the steps, because there are a lot of steps to this. And if we can tell ourselves the story, those steps are obvious. So we're looking for the intersection of L1 and L2. Now, for the purposes of giving a more generally applicable example, there's an obvious line, or an obvious orthogonal line I didn't pick. I didn't put in the perpendicular through the point C. In an exam, you absolutely would use this line that I've just put in as a green dashed line, because it's extremely easy to find once we've drawn our diagram, which we always do. So our line L3 would just be the line x is equal to 2. A very easy line to find, and a very easy line to use for finding the intersection of lines. So in an exam, if we get a horizontal or a vertical line, we're always going to use it because the equation is so simple and so quick to find when we've drawn our diagram. So again, the way these questions work, we draw our diagram and we tell ourselves the story of how we're going to construct this using the diagram. We're looking for the intersection of our lines. Well, if we're looking for the intersection of a line, we write down the line equation. So for L1, I'm looking for a line that is going to be perpendicular to AC and goes through the opposite vertex at B. So I've written down my equation, I've gotten this information from my diagram, and now I'm in a position where I know the story of L1, and I'm able to find all of the pieces for L1, and then find all the pieces for L2, and get the intersection of the two of them. And the picture and writing out my formula and how I'm going to use my formula gives me that story, gives me that structure, so that I don't make any mistakes. One side note before we dive into doing this question formally is a special case that can come up as a kind of a final question in one of these on the exam. So if when we get the intersection of L1 and L2, we find that it is one of the corners of our triangle, that tells us that we have a right angle triangle. So if we go down to the bottom of our screen here, and I have a right angle triangle, if we go, L1 here is the perpendicular to the vertical side through the opposite corner, and L3 is the perpendicular to the horizontal side through the opposite corner. Where they cross over each other is the bottom left-hand corner of the triangle. So for a right angle triangle, one of the corners of the triangle will be the orthocenter. And in an exam, they could ask us, well, the fact that you got one of the corners as being the orthocenter, what does that tell you? And it tells you you have a right angle triangle. So that's something to keep in mind as a kind of a final question in something like this. Now let's get into following our structure. So we have drawn our diagram fairly accurately. So we have a good notion as to the story. We've written down our formula because we're looking for the equation of a line. We've written down what our x1, y1 is. It's going to be the point B for L1, and the slope is going to be the perpendicular to AC. Now let's get the perpendicular to AC. So to know the perpendicular slope to AC, I need to know what the slope of AC is. So I write down my formula from my log tables, and I write down the points that I am going to use. -2, -3, and C is at 2, 1. And I have all of that information right next to me. I'm not looking across the page, and I'm writing down the formula I am using. And so when I sub in, it's directly beneath it, and I can see if I make any sign errors or anything like that. Because it's a very easy way to lose marks, and a very easy way to protect ourselves from losing marks, to write down our formula and then directly below substitute in our points. Otherwise, the chances of an error are very high. So I end up with 4 over 4, which is just 1. So if I want to know the perpendicular slope, it's just going to be either negative reciprocal of this, or m perpendicular times m is going to give me minus 1. So the slope I am looking for, in this case, is just going to be minus 1. It shouldn't have 3 lines in it. That would be for a proof, or a more geometric proof. Okay, so I know that my slope that I'm looking for L1 is going to be minus 1, either by using this formula or saying flip the fraction and change the sign. And now I know my point on my line, so I can now get the equation of L1. So I write down my formula and sub into it. So I know m is minus 1, and I have my point B is at 3 minus 3. That's my x1, y1. Note that I have a different x1, y1 going on now than I just did a moment ago. So it's important to keep rewriting this down so under exam pressure we don't make any mistakes in substitution. Minus 3 is equal to minus 1 on x minus 3. Y plus 3 is equal to minus x plus 3. And there's a few different ways that we can recognize this. We subtract 3 from both sides, and we can add x to both sides. I'm writing this as you would for a normal equation of a line that would be more complicated. Recognizing that this is just the line y is equal to minus x is perfectly fine, and you can do your simultaneous equations via substitution instead of doing your adding the two equations together, which is the structure I'm going to follow because it's what you will more often do. Now we have the equation of L1, so I'm going to make a note. That's the equation of L1 as I've drawn it. Now I need the equation of L2, which follows exactly the same structure. No difference whatsoever. So L2, I'm going to write out my equation. So I write down the equation of a line formula because I'm looking for the equation of a line. I write down the point that I am going to go through. I am going through the point A, and I know my slope is perpendicular to BC. I have my story told. I now know what I'm looking for. So let's find our missing piece of information, which is the perpendicular to BC. So we're just writing down our formula and subbing into it. So substituting in, writing down my formula, writing down my points, substituting in, I get the slope of BC is minus 4. And as I have my diagram drawn, it's worth just having a quick look at the diagram and saying, does that make physical sense? And if I go across by 1, I've dropped by 4. So that's a good sign. It looks sensible on my diagram. And I can also find the slope via the diagram saying rise over run. Now the perpendicular to that, again, we have our m perpendicular times our slope should be equal to minus 1. When we use that formula, sub into that formula and rearrange, the slope that we are looking for is going to be, I'll call it ML2, is going to be 1/4. So now I have my slope and I have my point on my line, so I'll write down my equation, my line formula, and sub in. When I write down my formula, write down my point, I have my slope right here, sub everything in. Now I see I need to get rid of this fraction. I never want to deal with fractions in equations if I possibly can. So when I have y plus 3 is equal to 1/4 on x plus 2, I'm going to multiply both sides by the lowest common denominator. And if there are multiple fractions involved, it's okay, because this can become quite messy. It's okay to do this in multiple stages. So don't shy away from doing this in multiple stages if multiplying by the lowest common denominator seems stressful in the moment. Do it out in 2 steps instead, because there's enough going on in these questions. It is very easy to miss something. So now this is just multiplied by plus 1, so bracket doesn't really change. Rearranging our equation into our standard simultaneous equations version would be minus x minus 12 minus 12. So I'd end up with minus x plus 4y is equal to minus 10. Now I did it in that order because I can see I'm going to add these two equations together, and now I have plus 1x and minus 1x. Saves a moment in doing the simultaneous equations, and I note to myself I now have L2. Just again to remind you, in the exam, if you recognized you had your vertical line here, you could just sub in x is 2 into this equation, and you would be able to find your values for x and y very quickly. We're going to do it out in this more general form, just so we have a more general example. But in the exam, if you spot something like this, absolutely use it. So we want the point D, which is the intersection, as we noted up here, the intersection of L1 and L2. So I am going to have just L1 plus L2. So that's going to be x plus y is equal to 0 and minus x plus 4y is equal to minus 10. So I add those together. And I end up with 0x plus 5y is equal to minus 10. Divide both sides by 5 to isolate y, and y is equal to minus 2. And again, that doesn't look ridiculous for my diagram, so I can constantly check back in on my diagram to see, does this make physical sense in terms of my construction? And then finally, I know x plus y is equal to 0. I now know y is equal to minus 2, x minus 2 is equal to 0. Rearranging, x is equal to 2, so I know my orthocenter is at x is 2, y is minus 2. And that is what I was looking for. And again, in the exam, if you spot something like this, there is absolutely no reason not to use it. This is purely to give a more general example in case you didn't get a nice line like that for finding your orthocenter. And again, if you found that this point was one of the points A, B, or C, that would tell you that you had a right angle triangle. In this case, the orthocenter is not at one of the corners, therefore we do not have a right angle triangle. And that's what we need for now.